Where did my answers go here? There they are. Okay, so check your answers here. We'll talk about any that you need to. Pull this down a bit so you can see a little bit more. You can write it either way. I don't care. I like using the E because it's easier to write, but as long as you can recognize what that means, I'm happy. Well, that wouldn't be correct because for scientific notation, you should only have one number to the left of the decimal. Okay? One number to the left of the decimal.
Okay, and then when would you want like full number?
In standard notation, but now here's the thing. There's no hard or fast rule on when to use scientific notation. Okay? You need to know how to use it. It's kind of up to you, but remember the whole point is to make numbers easier to write without having to write, 47 zeros or whatever. So, just as an example, you could write this number as 1.2 times 10 to the second, but why would you do that? That'd be kind of a waste. The whole point of scientific notation is to make things easier to write. Okay? That 1,200, that's not too hard. 1.2 times 10 to the third, probably not worth it. 12,000, maybe not. We start getting up here like this, though, and now maybe it's worth putting in scientific notation. Let's see. That'd be 1, 2, 3, 4. That'd be 5. This would be 6. 1.2 times 10 to the 6. Yeah. Around there, 5 or 6. That's when you probably want to start using the scientific notation. Other than that, it's kind of a waste, right? But you start getting more and more zeros on there, then it starts getting worth using. Yeah. Now listen. Obviously on this first test, I expect you to know how to do scientific notation. Beyond that, I'm not ever going to count answers wrong if they're in scientific notation. If you put 5 billion with all the zeros there, I might go, circle it and put a question mark. Why wouldn't you put that in scientific notation? But I'm not going to count it wrong, okay? But the biggest thing is, if I put numbers in scientific notation, you should know what that means, and we shouldn't have to go, wait a minute, what does that mean? Okay? That's the whole point of learning how to do this, because I'm going to put numbers in scientific notation if they're really big. Yes? True scientific notation means there's only one number to the left of the decimal. So here, this would not be true scientific notation because you got more than one number to the left of the decimal. So we got to move this over 2 more times. Okay. Yes. Exactly. Okay. Now, my rule, if you're adjusting any of these, my rule is always, the way I like to think of it, if you make the number smaller, so in this case we're moving the decimal over to make 1.2 instead of 126, then we should make our exponent bigger. So -3 is 2 levels bigger than -5. If we're making the number bigger, like in this case, we would move it over to make it bigger, then we need to make this smaller. Okay, any other questions on 1 through 5? Okay, good. Okay, here's number 6. So here, Sam, we're moving this over 3 times. Since we're making this number bigger, we need to make this exponent smaller by 3. So -11 is 3 levels below -8.
I was just telling you that if you don't show your work, you can't get partial credit. You got mad at me. You don't need to show work for this. There ain't no work showing.
Yeah, I mean, you could do the little loose. That might be. That's kindergarten.
Those ones are either right or wrong. Now these ones, Logan.
Yeah, here there's no work to be shown. You're just writing it down. All right, so check your answers here. We'll talk about anything we need to. I don't know where my erasing towel went. No. Only if there's a 0 to the far right. Right? Over on the other side of the numbers.
So is it like 0.900?
Then those two zeros would be. Right, but 0.009, there'd only be one. Okay, so see that 0 to the left, to the right of the decimal? Okay? There'd be no reason to write that other than to show that it's significant. Right? Because otherwise you just write 1,000. And then all the other zeros become trapped. Sure. Okay. All right, let's make sure there's no questions on 1 through 12, and then we'll go over some of these. Any of those we need to go over, 1 through 12?
Oh, I had 7, 4. I got number 8.
1, 2, 3, 4.
No, I had it right. Why are there 2 zeros by the decimal?
Because these are just placeholders. They're not to the far right. They're not out past the other numbers.
So could something get trapped at 4 in a decimal point, or is that not a point?
There can be. If this was a 1, then that would make those trapped. Okay? Yes?
On number 10, why is that last zero significant?
This one right here? Because it's to the far right of the decimal, right? It's out past the other numbers. So that makes it significant, and the reason is thered be no reason to write it if it wasn't significant. Nick?
Why are we learning about this?
Because it's going to come up in other science classes. And here's the thing. When we do calculations, we're going to get numbers that have, on your calculator that have 12 decimal places, and that's ridiculous. We got to be able to know how to round that off. Our rule is good. We're just going to round everything to 3 significant figures. But you need to know what a significant figure is to be able to round it to 3 significant figures.
Well, it's like 2 knowledgeable questions a year.
Okay? It's good to know.
Roark, I think you got that one wrong. But I'm just kidding.
All right, let's talk about these. Now, the first 4 here are all about multiplication, right? Product means multiplication. So here we're going to multiply these numbers together, but we got to write it in the correct number of significant figures. So remember, our rules for multiplication and division are your answer can only have as many significant figures as the least precise number you started with. So we look here. This one has 4 significant figures. Hey, be quiet. This one has 2 significant figures, so we need to round this off to 2 significant figures. That's why it's 1.1. Okay? In this case, right here, this only has 1 significant figure, so our answer can only have 1 significant figure. Remember, we don't take the zeros away, we just round it off so there's 1 significant figure there. Hey, guys, when other people are talking, it really distracts me. I can't understand what's going on. Oh, yes. If we needed to round this to 1 significant figure, then we would round it to 2,000. Yep.
So the answer for that was, like, the answer in the last time was 11,739. So how do you get 10,000?
Okay, we have to round this to 1 significant figure. That means we got to keep this one, and then all the rest turn to 0. Since this is a 1, we leave this be, and we get 10,000. If this was like a 9, then we would round it to 20,000. Okay. Right. If it's 1 significant figure, you keep the first number. If it's 2, you would keep the first 2. Okay. Yes, Matt.
I think you should go over the
Product means multiply, Nick.
Oh, yeah.
Logan,
Figure that out after.
question.
I seen the thumb down at the bottom.
How is that accurate whatsoever if the actual answer is like 11,739?
Because this was not very accurate. And if this number is not very accurate, then our answer can't be very accurate.
What if that's the actual precise?
Then you would have a bar over this, and we would round it to 3 significant figures.
Makes sense now. The world as we know it is wrong in terms of things going that far. Like in math,
Because in math, you're generally working with perfect numbers. In math, they assume the numbers are perfect. Remember, the whole reason we use significant figures is because there is uncertainty to all measurements, right? All right, yes, Alyssa.
Wouldn't you round number 17 to 21.4? What's the answer? Whoa.
Okay.
Can we just go one at a time? I need to.
All right. Let's just go one at a time. And yeah, I don't have an answer for 16 here. I think it got deleted. Yeah, well, we can work off of this. All right, listen. We're doing multiplication first, yes.
But are we doing, multiplication, subtraction?
Huh?
Yeah, division, subtraction.
Well, I just did multiplication and addition because remember the same rules apply for addition and subtraction. So if you can do significant figures on addition, you can do it on subtraction.
I guess.
Okay. All right. Number 15. The product of these two things, right? And here, this one has 3 significant figures, 5, 2, 0. So that's 3. This one has 4, so we need to round it to 3 sig figs. Okay? Now look, this is the same thing as here, as number 13. So 13 and 15 are the same. It's just we have an extra significant figure, so we need an extra number out there. Oh, here's why, actually, I deleted number 16, because it's exactly the same as 13. So this one should be 1.1. 2 significant figures. All right. Any other questions on 13 through 16 before we move on to the addition?
I kind of really forgot how to do the addition.
Yeah, me too. I had no.
Okay.
Now that I see your answers, I realize that.
Yeah. So remember, on addition and subtraction, what you want to do is you want to write the thing down in the, in the old school, put it right on top of each other so the decimal places line up. So I kind of show that here, but I'll redo it over here. So we would write 21.34 plus 0.052. Okay? And then you would add it. So we get 21.392. Okay? And then we have to look at what place do they agree. And that would be this place right here. So that's the last significant figure that we can keep. So we would cut the rest off. Because this is a 2, we leave it the same. 21.39. Okay? Yeah, got to keep the rules straight. Okay? Now, let's look at this next one. 523.478. So we get 523.478. Then we have to look, where do they agree? Well, this 0 is not significant, right? So this is actually the last place that they agree. Now, I know that can be a little confusing because this number doesn't have anything there, right? But we know that there's not supposed to be anything there. So basically, you just have to back up to the least place. So this is where we have to round it off on, so it's 500. And this kind of comes down to, remember yesterday I said if you're standing on a scale, right, and a fly lands on your shoulder, the scale's not going to read different because the scale is not precise enough. Here we're saying we have a measurement of 500, but it's pretty inaccurate. And so adding 23 to it is not going to change it that much because, we have so much uncertainty about what that measurement actually is. Okay, let's say this was 500 and we're adding 73.48. So this would be 573. Then we would round it up to 600. Right. To the last place where they both agree as far as precision goes. You mean right here? This 0 is not significant. So that they don't agree right there. This 0 is not significant. They do, okay? Because we know this is not, 173. These places out here, even though we don't write numbers down there, they're technically significant because. Right.
So if it was 510, would 530 would be the answer?
If this was 510, no, you'd round it to 500.
No, if that's the top one.
Oh. If it was 510 and we added this, we got 583, we'd round it to 580.
What's that bottom number?
7.
Oh, I thought it was, okay.
Yeah, I changed it to a 7. Sorry. Okay. Okay, and here, hopefully you can see 17 and 19, you get the exact same answer because the only difference is the 0. And yeah, that gives this number more significant figures, but it doesn't matter because for addition and subtraction, it doesn't matter how many significant figures they have. It matters where they agree on precision. So that was my point of putting that one on there to show that just because that has an extra significant figure doesn't mean anything. All right. Now we're going to talk about how spectrophotometers work, but first we got a concept that we got to learn, and that's concentration. Concentration. Well, we're not talking about atoms yet. Like I said, I want to get into this because we're going to use the spectrophotometer a bunch of different times. And the very first chapter, you're always just kind of reviewing a bunch of stuff, and it's kind of all over the place. Okay. It would be a good idea to write some of this stuff down and actually pay attention and quit talking.
Roark, I'm taking notes.
Awesome idea.
Concentration. I'm really good at that.
In this case, concentration is referring to the strength of a mixture.
Oh, sweet.
Okay, generally in chemistry, 99% of the time when we talk about concentration, we're talking about concentrations of a solution. Okay, you can talk about concentrations of like suspensions and colloids, but we're going to talk about solutions. For a solution, we have two terms we need to define. There is solvent, which is the substance that is doing the dissolving. And then there is the solute, and that is the substance that is being dissolved. Angry typing. If you've ever made Kool-Aid, you've made a solution. What would be the solute?
Sugar.
Yeah, like the sugar and stuff. Okay, what would be the solvent?
Water.
Water. Okay, in the majority of cases, the solvent is going to be water. Okay? You can use other solvents, alcohols. There are some non-polar things. But for most of the stuff that we're going to do, you're going to use water as your solvent. Does it always have to be a liquid? That's a good question. No. You can definitely make solutions of gases. That's a little hard with the stuff that we have. Yes? In certain cases, you can actually dissolve stuff into solids, although that's much more rare. So most of the time it is going to be a liquid, and most of the time it's going to be water. Plasmids and gases don't behave that much differently. That it's actually more variable. I would say more solids than liquids, but definitely a lot of liquids can be too. Okay, and actually also gases. Hey, listen. For example, fish breathe oxygen straight out of the water. There is oxygen that is dissolved in the water, and their gills are made to extract that oxygen. So there, the solute is the oxygen gas, and the solvent is the water. So it would probably be good to write this down, because it seems like this table only pays attention to what I'm saying if there's actually stuff on the board. Now, we calculate concentration by taking the amount of solute and dividing it by the amount of solvent. There are different ways of doing it, but the standard way that we're going to do it is we're going to measure the amount of solute as a mass in grams.
Is that like sugar?
Right? If you wanted to make sugar water, you would measure the grams of sugar. And then the amount of solvent is going to be measured, the volume, in milliliters. Now later on, after we learn about moles, we will have a different way of calculating concentration for molarity. But for right now, this is how we're going to do it. So yeah, if you want to make sugar water, you can measure out a certain amount of sugar, and then, on a scale, a mass of that, and then a certain amount of water in like a graduated cylinder or something, mix the two together. Now here's the thing. Concentration is a ratio, which means you can make the same concentration multiple different ways. So you can put 5 grams in 100 milliliters. You can put 2.5 grams in 50 milliliters. Those would have the exact same concentration. You would just have more of one solution than another. Because it's a ratio, there's no one way to make it. It depends on how much of that solution you want to make.
So, doing this stuff, does that mean we have to do those conversions?
You shouldn't have to do any conversions here because, in this case, you're going to measure things directly in grams on a scale, and then you're going to measure things directly in milliliters using the glassware that we have. Generally, yes. There are other ways of doing it, but that's the standard way we're going to do it. Okay, so it is a ratio. So that's good to know, just to kind of start out, because what we're going to be looking at, the whole point of a spectrophotometer is it is useful for finding concentrations of things. So let's explain what a spectrophotometer is. All right, so this is what our spectrophotometer looks like. Actually, behind Sam is a spectrophotometer, although, no.
Does that look like what's on the screen?
Yeah, that thing. Okay. That spectrophotometer is older. It is broken. It does not work, so I bought a new one. Okay. The whole point of the spectrophotometer, and what the word tells us, is it actually uses light, and spectrum means it can actually pick out certain wavelengths of light, and we're going to use it to analyze certain samples. So a spectrophotometer is a piece of equipment that is used for what we call analytical chemistry.
Is this what we're doing in our lab with tomorrow?
Yes.
So there's only one of them, so it'll be a big old group project?
Well, we're going to have different groups. There is only one of them, so we'll have to go quick. Not in a half an hour. I said I haven't tried it in a half an hour. I can?
Wait, does that mean I have parts in my iPad? No.
I haven't given it to anybody yet. I want to see what it says. If it doesn't work, it doesn't make sense.
See, like, I do it through ViewPeer, but it'll come up like this, then you hit play. And then, yeah. So this video is restricted. It says try signing in with a Google Apps account.
That has nothing to do with our network. They're restricting that video. I'm telling you, it has nothing to do with our network. If it did, it would say, what would come up, it would say, this is being blocked by Meraki.
I get that. But, I used this last week. I mean, there's no, like, weird blocking on this. This is just like a...
It's strange, but for some reason that video is unavailable.
Nah, I don't think it's YouTube.
It's not our network. Because it's unblocked. I can get on YouTube right now on my laptop and go anywhere I want.
Well, I don't understand why my computer isn't.
Can you send me that URL?
I can.
Send me that URL.
We can try it. We can try it on here.
Yeah, try it on there, and then I will try that specific one.
I mean, I feel like it. I don't know.
I can tell by that message that it's not our network. Because if it's our network, we have a specific thing that comes up.
Yeah.
It says this is being blocked by Meraki.
Okay, listen. I am working on this. Be quiet.
As long as it's on his phone, I don't care.
Well, yeah, how am I supposed to go on Snapchat, Instagram, and Twitter?
Let's see how far it goes. Yeah, video unavailable. That's odd.
I've used that lots of times, and there's other things that are coming up too. And at home, you can get on it just fine.
But you can't hear.
Yeah.
That makes no sense.
It's like it's like my account.
It's like your video account. It's like your YouTube
is being
account.
blocked for some reason,
Right.
but I don't know why that would be.
It makes no sense. It makes no sense. Can you get to a different video?
There's some that come up. Yeah. There's certain ones for some reason.
That's odd. So, because if it was blocked, I'm telling you, none of them would come up.
Yeah.
That's what's strange. I will. Can you send me this right here?
Yeah.
A screenshot of that?
Sure.
And then I will investigate what that's saying right there.
Yeah. And this is through ViewPeer, but if you go to just YouTube, right?
Right.
And then you search.
Right. View.
Well, no, you just search for that D News, and this is a video I've used.
Right. Many times.
Many times.
Right. Sure.
Let's see. It doesn't come up, and I don't know. Like when I do it on the computer, it'll say, certain video, or it'll say search results restricted, see your network administrator.
Oh, I know why that is. It's because of the content of the video. Our filter is so specific. I mean, it's just like with JP.
Yeah.
There's certain things he can't show because our network is so restricted based on keywords. That's what's weird.
Well, what's weird is like some videos will come up, and then a video that is like a second part of that won't.
That's yeah, I've seen that before too. Shane Lee had that problem last year.
So I mean, is there any way to get around that? But why would it change from this year to last year? That doesn't make any sense either.
That doesn't make any sense. Send me that screenshot.
Okay.
Let me look into it. Let me see if I can fix it.
Okay.
All right. Thanks, Dave.
Yeah, thank you. All right, back to spectrophotometers.
Get back to work.
You want to learn about spectrophotometers?
I'll be on the other side. Throw it. Do it.
All right, analytical chemistry is kind of a branch of chemistry that basically deals with, guys, the whole point of analytical chemistry is to detect certain chemicals in samples. And that can range from all sorts of things. Chemicals in samples. Now, that can come down to if a geologist has a piece of rock and he wants to know what types of chemicals make up that rock. An analytical chemist would break down the rock and be able to analyze that. Certain things in the human body, in the atmosphere, all that sort of stuff. Okay? So the analytical chemistry, some people like it because it's sort of like a mystery, right? What is in this stuff? How much of it is there? We got to be able to figure that out. And that's one of the things that we're going to try to learn how to do using this machine. Okay. Inside the spectrophotometer, we should probably write that word here. And if we break this down, photo means light, spectro means a certain portion of the light, and meter means measure. So this machine is basically measuring things using light. Okay, the spectrophotometer has a light source. I'll show it to you when we look at the spectrophotometer in the back. It's basically just a bright halogen bulb. The light source gives off all different wavelengths of light. So all the different colors of the rainbow are given off by that bulb. Okay, there's going to be a lens that is going to focus it. So think about taking a magnifying glass and focusing sunlight. Okay, and then it's going to throw it through a prism. That prism is going to split it into the actual different colors. So it's going to separate. So all the red is together, all the purple is together, all the green is together. And then we have a wavelength selector. And I'll show you on the back, you can change it to a certain wavelength. And the wavelength is going to be the color of the light. So we'll see on there's a scale, and it'll show you, okay, red light is this wavelength, purple light is that wavelength, whatever. That light, this thing is made so that it will only select one single wavelength of light. So you're getting one color of light that comes through, and that goes through your sample. Now here's the way this works. If there's nothing in here, then the light that comes through should not get blocked. But if there are particles in here, even things as small as sugar, right? Sugar you can't see with the naked eye, but it will absorb some of the light as it goes through. So as it goes through, some of the light will get absorbed. So if we can measure how much of the light gets through, we can actually use that to figure out how strong this is, what the concentration is. The stronger it is, the more light will get blocked.
What do you want to measure how much light got blocked?
Right. So there's two different terms here that we're going to define.
I have a question.
Yes.
Why and how is that thing spinning right there?
Oh, well,
It's on the inside and the outside. The light hits it and makes it spin. But if you turn off the light, But I don't think it would spin in the other thing. No, you can hold it and it will still spin.
Well, it's got an outside layer, right? It's got like a plastic thing around the outside, then it's filled with liquid, and then there's the sphere on the inside. The light hits a photocell, hits a solar panel, and it creates a little magnetic field, and then that pushes on the Earth's magnetic field and makes it spin. Okay. Yeah, when the lights are on. Yeah, when the lights are off, then the solar panel doesn't do it. Yes. Okay, listen. There's two different terms here. Absorbance and transmittance. Okay? Absorbance is the calculation of how much light is blocked. What?
That just sound alien.
Great. Okay, transmittance is the opposite of absorbance, and it is related to how much light goes through. And transmittance is going to be usually calculated as a percentage. Now, Matt, you said, wouldn't it be useful to measure how much light is blocked? That's true, but you can't directly measure that. All you can measure is how much light actually gets through. We have to be able, we want to relate that to how much gets blocked, because that'll tell us how much stuff is in there. Yes. So we're going to measure this. Basically, the spectrophotometer is going to measure this, and from that we can get the absorbance. And you'll see they give you both values on the actual spectrophotometer. What's that? Well, no, it shouldn't be less precise. Yes? Yeah. We're actually going to the back here, so.
You're going to do what?
Well, I'm taking these guys to the back.
Oh, you are? Oh, good. That was good timing then.
Yeah. Just let me, here. Here's this. Just a minute, I got to stop my recording.
Oh,
Stop my